Peter Karori from Mount Kenya University. I'm bringing to you the unit on Organic Chemistry 1, BCH1108. And this will be lesson 1 of the unit. So I'll start by introducing the course content. So the course content starts with the introduction to organic chemistry. In the introduction to organic chemistry, we look at general organic chemistry and hybridization, elemental analysis, and hydrocarbons. Then we have alkenes, sources, nomenclature, structural isomerism, physical properties of alkanes, chemical reactions, mechanisms of free radical substitution, cycloalkanes, nomenclature, geometric isomerism, preparation of alkenes. Then the next subtopic is on alkenes. It will be on sources, nomenclature, structural isomers, and geometric isomers, that is the cis and trans isomers. We also look at physical properties, chemical reactions, preparations of alkenes, qualitative analysis of alkenes. Then we have a subtopic on alkynes, that is sources, nomenclature, physical properties, and chemical reactions. Then the last part on course content is on functional groups, that is functional group chemistry, that is introduction to functional groups, including alcohols, carboxylic acids, ketones, aldehydes, alkyl halides, and aliphatic amines, as well as phenols and ethers. The references, the reference books that you can rely on are Organic Chemistry by Wade L.G., Organic Chemistry by Wilga, Organic Chemistry by Morrison and Boyd, Fundamentals of Organic Chemistry by M.C. Murray, Organic Chemistry by Solomon, and Organic Chemistry by Francis Curry. So for the lesson 1, we shall basically deal with the first subtopic, that is introduction and hybridization. So now, in terms of introduction, organic chemistry is a branch of chemistry that studies the structure, properties, and reactions of organic compounds. That is their structural nature, chemical composition, and physical properties. Now, chemistry generally is a very wide subject, which has 2 major branches. And one of the major branches is organic chemistry. The other major branch is inorganic chemistry. So in this case, we are looking at basically the principles of organic chemistry. And considering that organic chemistry is a major branch, then as a way of definition, the purpose and the reason why organic chemistry is considered a major branch of chemistry is in the sense that very many substances in earthly life are constituted of organic chemicals. That is, many commercial products in pharmaceutical industries, petrochemicals, that is in industries, and agri-chemicals. When we talk about pharmaceutical compounds, then we are talking about areas of medicine. Now, in terms of definition, organic chemistry is the chemistry of carbon compounds. Now, on the periodic table, we have over 100 stable elements. And Organic chemistry is basically the chemistry of carbon compounds which are covalently bonded. So the first question that one would ask, why would we study the chemistry of one element separately from the chemistry of all other elements, which are much more? Yet that element is not even one of the most abundant. And the reason is simple. In terms of different compounds that are known, organic compounds constitute more than half of all those known compounds. In fact, we have more than 10 million known organic compounds, and yet others are yet to be discovered, including the capacity to be synthesized. So the first question we shall ask is, why does carbon have so many compounds? And the answer can be in 5 points. Point number A is that carbon, having an atomic number of 6, has the general electronic configuration of 2,4, meaning that in the inner principal quantum shell, carbon has 2 electrons, and in the outer principal quantum shell, carbon has 4 electrons. Now, what happens is that carbon is able to use all the outermost electrons in bonding, in covalent bonding, meaning that carbon displays tetravalent character, and forming octahedral bonded compounds. Now, the other reason for why carbon has so many compounds is due to its ability for catenation. Catenation basically means that an element has the capacity, atoms of an element have the capacity to join with one another, forming long chains and rings. So, meaning that you can have very different elements, compounds from the same elements. Another point about carbon is that carbon has the capacity to form different types of bonds with itself. It can form one bond, that means sharing of one pair of electrons, which we call single bond. It can form 2 bonds, meaning sharing of 2 pairs of electrons between 2 carbon atoms, which we call double bonds, or it can form 3 bonds. That means sharing of 3 pairs of electrons, and which we refer to as triple bonds. The other point number 4 is that carbon atoms with identical molecular formula. You may have the same number of elemental components in a carbon compound, and yet you have different carbon compounds. That is due to different joining or constitution of those elements, or the way they are oriented in space. And this is what generally is referred to as isomerism. So that is, we can say that carbon has the capacity to form very many different types of isomers, more than any other element. And the last point is that apart from of being tetravalently bonded, carbon does not only bond with other carbon atoms, but can bond with atoms of very many different elements, mostly hydrogen, oxygen, nitrogen, in that order, and even many more, which may be in lesser prevalence. Now, we have said that carbon has an atomic number of 6, meaning that by considering Hertz's rule and Aufbau's principle, then the electronic configuration of carbon should be, in terms of principal quantum shells, 2 and 4. 2 and 4, meaning that the inner principal quantum shell has 2 electrons. Those inner electrons do not take part in bonding. So what we are interested in are the 4 electrons in the outermost shell. Now, in terms of SPDF electronic configuration, you'll find that the principal quantum shell number 1 has 2 electrons in an s suborbital, while the outer principal quantum shell, that is shell number 2, is supposed to have 2 electrons in the s suborbital, because you must fill the s suborbital before you fill the p suborbital, which is a higher energy orbital. So ideally, carbon should have an electronic configuration of 1s2, 2s2, 2p2. What that means is that because an s orbital has only 1 orbital, and electrons are supposed to pair before they start, are supposed to join singularly before they start pairing up. When it comes to principal quantum shell number 2, the s orbital will have a pair of electrons, but the p orbital, which is able to hold 3 pairs of electrons, px, py, and pz, will have 2 electrons, which should go to 2 of the orbitals, meaning that 1 of the orbital will have no electrons. In that case, ideally, in the ground state, carbon should have 2 unpaired electrons in the principal quantum shell number 2 in some of the p orbitals, and so the unbounded electrons should be in the p orbital. But then, in that kind of a situation, carbon would then not be able to be tetravalent. So I was saying that considering the electronic configuration of carbon, then we should have in the outer principal quantum shell 2 unpaired electrons and 2 pairs of electrons, meaning that there are only 2 electrons that can bond covalently. In that case, carbon would be divalent, and it would have a lone pair of electrons which can be involved in dative bonding, and again an empty orbital which can accept a lone pair of electrons for dative bonding. So it would only be tetravalent if it involved dative bonding. But in reality, we know that all the 4 bonds in carbon are covalently bonded, and carbon rarely exhibits dative bonding. So how is that explained? And the explanation to that behavior in carbon is through what is referred to as hybridization. Carbon has the capacity to hybridize. And hybridization basically means mixing of atomic orbitals. And there are 3 major types of hybridization in carbon. The most common one is SP3, the second one is SP2, and the third one is the SP hybridization. Now, we shall look at the 3 types of hybridization. And hybridization basically means mixing of atomic orbitals. So how do the atoms, the orbitals in carbon mix so that you can either have SP3, SP2, or SP type of hybridization? Now, before we go to the specific types of hybridization, is that when carbon is SP3 hybridized, all the bonds it forms are single bonds. That is a single carbon to carbon or carbon to another element bonds. And the bond angle is 109 degrees because it forms tetrahedral structures. When carbon is SP2 hybridized, the resulting molecules are of the form of alkenes, and the Bode angle is 120 degrees, and the type of structure is trigonal planar. While when we have SP hybrid orbitals in our, we usually form hydrocarbons of the form of alkynes, and the Bode angle is 180 degrees, and the molecules are linear. So we look at each type of hybridization, starting with SP3 hybridization, which is the most common in most of the single-bonded carbon compounds. Now, we are saying that in the ground state, where a carbon atom has 2 electrons in the 2s orbital and 2 electrons in the 2p orbital and an empty p orbital. What happens is that because of the stability established by forming equivalent bonds, there is a step where the orbitals undergo excitation, an excited state, so that the electron in the 2s moves to the 2p, so that you have 4 unbonded electrons. Now, the 2s would be at a different level from the 2p. So the third step involving mixing of the orbitals so that the energies are equivalent, so that we have 4 orbitals, 1 from the s suborbital and 3 from the p suborbital, so that you end up with 4 orbitals, one which is an s and 3 p orbitals, what is referred to as SP3 hybridization. In that case, we have 4 orbitals with single electrons of equal energy, and that is what results in carbon-to-carbon single bonding, which, or even carbon to other elements single bonding. Now, an s orbital is spherical, while a p orbital is consists of flaps. So what happens in hybridization is that the one s orbital, it contributes its character to all the other 3 p orbitals, so that in an sp3 hybrid orbital, we have a character which is a quarter s and a 3/4 p. So 25% in an sp3 hybrid orbital is s character, and 75% is p character. So the important thing is the type of bonds that are formed. The type of bonds that are formed in sp3 hybrid orbitals are spherical bonds, what we call sigma bonds, bonds that are capable of rotation, and these are the bonds that you find in carbon to element bonded either to itself or with other elements in single bonding. Now, we go to the second type of hybridization, which is the SP2 hybridization, where we form what we refer to as SP2 hybrid orbitals. Now, again, we look at the ground state, similar. The excited state, similar to what we saw in SP3. But what happens is that in SP2 hybridization, only 2 of the p orbitals are able to mix with the s orbital, so that 1 of the p orbitals is left unhybridized. So a p orbital in an hybridized state generally forms pi bonds. So in this case, we have the capacity of forming 3 sigma bonds and 1 pi bond. And this type of hybridization happens where we have carbon to carbon double bond or carbon to other elements double bonds. So in that case, we are saying we have 2 p orbitals and 1 s orbital bonding to form 3 sp2 hybridized orbitals. And in that case, we end up with trigonal planar molecules with Bode angles of 120 degrees. In that case, those sp2 hybridized orbitals will have one s orbital bounded to two p orbitals. And what that means is that a third of the character is s, and 2/3 of the character is p in sp2 hybrid orbitals. And we say that what happens is that the p orbital, which is involved in pi as a pi bond, because can bond to a next carbon p orbital to form pi to pi bond, a single pi to pi bond, while the rest of the three orbitals usually will form a single bonds. Two will form single bonds with other elements or with another carbon, while one will be involved in a carbon-to-carbon sigma bond. And one of the simplest examples in sp2 hybridization is in ethene, where we have a carbon bonded to another carbon through a double bond, one being a pi bond, the other one a sigma bond, while the two other bonds in each carbon are sp2 hybrid bonds. Now we go to the third and the last type of hybridization, and that is SP1, or what can simply be referred to as an SP hybrid orbital. In that kind of hybridization, again, the ground state is similar because we are dealing with carbon. The excited state is where one electron moves from the s orbital to the p orbital. Now, what happens is that only one of the p orbitals in sp hybridization or in SP1 hybridization will join the s orbital. So in that case, the hybridization will involve one s orbital and one p orbital, and that is why it's referred to as sp. And we shall have two unhybridized p orbitals, meaning that we have the capacity to form two pi bonds. In each of the flap in this, so each is a flap, shows a p orbital. So we have each carbon having two p orbitals bonded to the next carbon, and as one of the s orbital, the sp orbitals joins in the carbon-to-carbon bond. So in that case, we have three bonds. That is where we have carbon-to-carbon triple bond. So only one of the sp hybrid orbitals is involved either in joining the next carbon or joining any other element in a carbon to carbon single bond or a carbon to carbon to other element single bond. For example, in ethane, where we have three carbon-to-carbon double bonds, we have two carbon-to-carbon double bonds, three carbon-to-carbon double bonds, with one being a sigma bond because it is an sp hybrid orbital, and two being pi bonds because they are formed between p electrons. So we have two pi bonds and one sigma bond between the carbons, and a sigma bond between carbon and the next element. So in that case, that is basically covered the topic on introduction to organic chemistry, and also the three types of hybridization. And we complete the introduction lesson by looking at exercise questions, which can help you in exercising and looking at your ability to understand the lesson. One question is, why are the hybrid orbitals during hybridization better than their parent orbitals? What is the difference between SP, SP2, and SP3 hybridization? What is the percentage of S and P characters in SP1, SP2, and SP3 hybrid orbitals? Then question number 3, explain the three basic shapes of hybridization in carbon. And then that question is explain SP3 hybridization in methane. Another question you should be able to answer is discuss results in SP2 and SP3 hybridization. Now question on introduction, define the term catenation and give 2 reasons why carbon catenates. Another question you should exercise and research on is indicate the type of hybridization for the carbon atoms in the following organic molecules. And you have 2 organic molecules. So one has 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. So you should be able to give the type of hybridization in each of them by stating whether it is SP3 hybridized, SP2, or SP1 hybridized. Then you have another molecule also with 1, 2, 3, 4, 5 carbon atoms. In each, you should be able to tell whether you can number the carbons as 1, 2, 3, 4, 5 and give the type of hybridization in each. Thank you and stay safe. Asante sana.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.